Okay, so the final speaker of today, we're very happy to have Francisco Rojas, who will tell us about celestial amplitudes and IR divergences in nonabelian gauge theory.
Okay. Okay. Thank you so much for the invitation and the opportunity. Okay, so I will, as the title says, I will say a few things about. Actually, strings will be my last few slides. So I'll just say a few things about string, and maybe I will talk more about the second part, which is the universal structure of IR divergences for the case of non-abelian gauge theories. Okay, so this is in collaboration with my collaborators here. Loga, Hernan, and Andrea are here in the room. Okay, so the outline of the talk is so field theory and then string theory a little bit at the end. So within field theory, I will first review what it's known as the all-loop factorization of the infrared divergences. Both I'll just say a few things about the gravity case and the massless QED case, and then I will come to the more, the center of my talk, which is in the case of non-abelian gauge theory. Then I will just show you how this factorization that happens in momentum space also persists in Mellin space after the Mellin transforms. And because of this universal subfactor here, I'll say more things about it in a few minutes. Because of this universal subfactor here is, hence as the word says, universal, it looks like a good place to look for universal features of the putative celestial CFT that we're all after. In that sense, this is a very complicated object, so I will rely on the large N expansion maybe to find some structures, some known structures in these theories. And then at the end, I will just say a few things about, sorry, is that my phone? Okay. Okay, I'll just leave it away. Far away. Okay, sorry about that. Okay, and then at the end, I'll just say a few things that we've done with collaborators also on celestial amplitudes for string theory in the case of tree level in one loop. And maybe I'll just focus on the last thing a little bit more about. There seems to be a mapping that emerges from the worldsheet CFT and the celestial CFT, but that's in its infancy yet. Okay, so the main part of the talk will be this. So in gauge theories and in gravity, infrared divergences are known to exponentiate. Weinberg's famous paper of 1965 showed this for the case of QED and in the case of gravity. And the factorization pretty much looks like this, that all the infrared divergences to all loop order exponentiate and become this soft collinear factor over here. And the nice thing about that factor is that it's universal in the sense that it's pretty much for every theory that has photons or gravitons, it has the same form. And it gets multiplied by this hard factor, which is by any means universal. It depends on the theory, and even more, it depends on the process, the scattering process that you're computing. So the central object would be the soft collinear factor in this talk. So let me give you like the results for a case of massless QED. For example, these Q1 and QI and QJ are the electric charges. And then the whole set of all loop infrared and collinear divergences exponentiate to this factor over here. Pi.pj are the Mandelstams, and here you see the hard part that I was mentioning before. Alpha is it's the coupling, the QED coupling, times this infrared divergent regulator. So you send the regulator to 0 at some point, and then that is the divergent part. Okay, and in gravity, you have something very similar to this. Again, but now here you have G Newton, but the structure is very similar. Instead of having the multiplication of the electric charges, now you have the multiplication, the Lorentz product of the momenta, but the structure is very similar. Now, even Weinberg in that paper already says that this was not going to work for the non-abelian case because of the intricate nonlinearity of gluon interactions among themselves. Okay, so let me show you the case for SUN gauge theory. This was developed thoroughly by Gardy and Magnier in 2009, and Becker and Neuber also in the same year. So now the soft factor has this form. So again, you see that it looks like an exponential, but it's a much more complicated exponential. It's an exponential of an integral of a matrix, so that needs the path ordering. And the central object here, it's what's known as the cusp anomalous dimension matrix. Okay, and but one of the things that are under control is that this object here, which is the central one, is actually infrared finite, and all the infrared divergences actually start to emerge when you compute that integral. And also, let me mention that the double line here denotes that this is a matrix, so it's called a matrix in color space. So the amplitudes are actually vectors in color space, and this is usually known as the Catani-Seymour color space formalism. So everything will be written in that form. Okay, so a few details. So for example, consider an n-gluon amplitude with color matrices associated to each of these gluons. There's color conservation, so this actually this is a little bit misleading in the sense that this is true when acting on the amplitude. So when it acts on, for example, the hard part of the amplitude, that is zero. So that's what's known as color conservation in this case. And let me show you what is how does this object, which is the important one, how does it look like? So this contribution comes from, it's basically a one loop integral, but then you get extra terms. So these ti.tj are this, this vector it's there. So the vector index will be the color index. So you build this vector looking things. And then you have this ti.dj log of that. So that comes from a one loop integral, just like in the case of the abelian gauge theory and also in gravity. And then you have this factor here, which is the nice thing is that it's proportional to the identity matrix, so it's simpler in that case. And this has all the information about the collinear contributions. And then you have extra pieces that start appearing actually at 3 loops. People, where they were computing these things, they realized that the 2-loop contribution was 0. So there was the hope that maybe the same thing that was happening in gravity and in QED, in which it's 1 loop exact. The hope was similar there, but then Simon Caron-Wood crashed that hope, saying that in that paper that there should be a contribution starting at 3 loops, and even it has to have this form. It should only depend on this ratios of Mandelstams that if you write them in the celestial, in the typical celestial, parameterization that we use for momenta, becomes that, and that's also an SL2C invariant quantity. And then, 2 years later, Amélie Dour and Gardy actually showed that what Simon was saying was indeed true. Okay, so that's not the end of the story. There's a 4-loop contribution, and that's the state of the art so far. This is in any nonabelian SUN gauge theory. So n equals 4 as well, yeah. But this is for the general case. So QCD. Okay. So, and this 4-loop contribution was found recently by Becker and Neuber in 2019. And okay, so yeah, this is what I was just saying. That starts at 4 loops. It's fully known. I forgot the reference. I put it later on. But this was done by Johannes Hahn and Misselberger also in 2019 for the case of n equals 4 Subier-Mills, and also for the case of QCD. They have the full expression for this guy for thinking in QCD. Okay, so let me put again the formula, but now let me do it. Let me rewrite this in celestial coordinates. So we use the usual parameterization. The Mandelstams become that, and then just for the moment, let me forget about the 4-loop contribution. Let me just work with the first 3, 1 loop, 2 loop, which is 0 and 3 loops. just for the moment. I'll come back to the for loop contribution later on. So that yields this after just a few algebraic manipulations, for example, using color conservation and using the fact that here you have this quadratic Casimir, which is proportional to the identity again. And in the case of gluons, you know, in the you get that the Casimir pretty much is equal to n. And then you get this nice looking expression over here. And the important thing that I wanted to stress is that this is the exact same thing as before, but now the Mandelstoms become these angles on the celestial sphere. And the extra piece is something proportional to the identity. So that path integral actually becomes immaterial. So you can compute things. And it depends on the energy of the external particles in that very simple way as a log of those energies, which I'm just mimicking what Ana Maria, Monica, Andy, and Nima did in a paper for gravity and QED. This is just the extension for nonabelian gauge theory. Okay, so let me put all this into the soft collinear factor with the path order and everything. And then, as I mentioned before, that now you can compute this in a straightforward way. Again, the only thing that depends on the energies of the external particles becomes this simple-looking product there. And now we really go celestial in the sense that now I'm going to compute the Mellin amplitudes. I'm sorry, the Mellin transforms on this full factorized form of the all-loop amplitude in nonabelian gauge theory. So here I'm just going to use what I had in the previous slide. This thing factorizes into two parts. This is just a celestial data kind of looking thing, so I can bring it outside of that integral. And then I just need to compute that Mellin transform of the hard part. But you see that this factor here only shifts the scaling dimension of the original scaling dimension of the external particles, and it modifies it with an infinitely large shift here because this is IR divergent. I didn't say any much details about it, but this is by definition this integral over here, and okay. That's infrared divergent. And this is also the same structure that Darkani Hamed, Pate, Reclary, and Strominger found for the abelian case in gravity. So that's nice. I mean, in the sense, let me just emphasize again, this is what I put in the little square here, that the factorization that you have in momentum space persists also in Mellin space, let's say, or for the celestial amplitude. Okay, so let me go back to that little factor that we left out. So what about that for loop contribution? So it has this nasty looking form in the sense that the matrix structure, the trace structure, it's very convoluted. But the nice thing is that, again, the only dependence in the Mandelstoms come with logarithms. So I can play the same game again. And then this is just going to be, if you go back here, I'm sorry, it will just be, you know, another omega of a different now factor here or exponent. And this is going to shift again the scaling dimension by just another factor, okay? And and also a nice thing, okay, maybe this is not very relevant, but for example, the new integral that we obtained there gets modified by an extra factor, and this is exactly the for loop correction to the Caspar nominal estimation that Henn and Misselberger found in 2019. But this is the thing that I want to stress the most about these slides, is that all loop corrections, I mean, Gardi and Magnier showed a long time ago that actually all these loop corrections must be of the form of logarithms of the Mandelstoms. So this would mean, and then that all higher loop corrections to all orders, all these infrared effects simply renormalize the scaling dimension of the celestial amplitude. That's all it does. And this is actually an equation that it's proven non-perturbatively by Gardi and Magnier. Okay. So since this universal factor is, again, universal, then it looks like a good place to look for, again, some universal features that we're after for the putative celestial CFT. And we also show that this is persist in the conformal basis. So let me study this new object or celestial new object in more detail. Okay, so moreover, what we're going to try is to search for a system of equations that maybe give us some guidance about what is the celestial CFT controlling the infrared structure of non-abelian gauge theory to all loop orders. So again, this is a very complicated object because of the matrix structure, but in order to get some to get some grasp on it a little bit, let me go first to the large and limit to see what we can do. So in the large and limit, the SUN generators. So these are going to be in the adjoint for sure. Of course, for external gluons, if I'm looking at an amplitude with external gluons only, so these are in the adjoint. So what happens is that. So remember that. Let me go back a little bit for at the beginning of these slides. So remember that the soft factor is acting on the hard part of the amplitude of this hard vector. So that Z is a matrix, of course, and then at the end of the day, you have to expand that exponential at some point, and when you expand it, then it looks very complicated. But if you look at the large n limit, if you do an expansion in 1 over n, you would see that at leading order, this combinations that appears from this part of the exponent projects the hard part into just a structure that only has single traces only, single traces. And when acting on the hard amplitude at the end of the day, you can make this replacement. Okay, I mean everything is. I mean you can do it, in a controlled way, but basically this is what happens. So notice that there's a factor of n there, and also it's proportional to identity. So again, the path order exponential, it becomes easy to do. So just as a summary of this thing, so the Ti.Tj actually gives you the dominant part, and the thing that starts at 3 loops and the thing that starts at 4 loops, and anything beyond that order are actually subdominant in the large n limit. So it seems that things are under control in a 1 over n expansion. So in that limit, I can compute that explicitly. I did the integrals, the path order, which is it's trivial, and we arrive at that object that is there. So if you look at it a little bit, you realize that this is what's called the partition function for a Coulomb gas. But notice that because of this Kronecker delta functions here, this is a Coulomb gas with the particular thing property that it's only for nearest neighbor interactions. So how can you get that? I'm sorry, what? Oh, I know. I've just took it from the yellow pages in the differentiesco. The partition function for
Yes, but in that case it's Coulomb because the interaction is in long range.
Oh, you're saying that? Okay, it's a semantic. Okay, then the name maybe is not.
It's not a Coulomb gas.
I agree. Yeah, I agree. Yeah. That quote unquote. I'm sorry. Yeah. Thank you. Yeah. Okay, so how can you get? Let me just review these things. Like, for example, the z, you can arrive at that z from from that 2-point function. Then you compute a vertex operator, which looks like this. So you have to define these colored scalars now. That's a color index there, and then they have a 2-point function that has that form. Again, this is mimicking what Andy, Nima, Monica, and Ana Maria did for the abelian case and gravity case. It looks exactly the same, but now the only new ingredient is now you have this colored scalar fields, and then you compute this correlation function of these normal order vertex operators, you get exactly that, that Z over there. Okay, and actually Lorenzo Magnier arrived pretty much at the same conclusions the same week as us, using the diaper approximation, which is basically the same thing that we did. The diaper approximation is the leading term in the 1 over n expansion, so that's why we arrive at the same. I mean, the calculations were pretty much the same at the end of the day. So just an observation, why, I mean, where is this nearest neighbor, interactions, why do they appear? So actually this is a direct consequence of the planar, large n limit that people have known for a long time. This is taken from this very nice review by Lance Dixon, Scattering Amplitudes, the most perfect microscopic structures in the universe, mimicking Chandrasekhar's macroscopic for black holes. So in the large n limit, so this very complicated, so the full amplitude, when you study the soft divergences, you see that there's an intricate set of diagrams of gluons that have the soft part, the hard part, and they all interact among themselves. But in the large n limit, only the neighboring gluons are the leading ones in that expansion, the 1 over n expansion. So, so yeah, that's the origin of the nearest neighbor structure. So now the natural question is, okay, what if I go beyond? What if I compute 1 over n corrections to this thing? Can we do it? Yes, it's very complicated, but in principle, there's no obstacle for doing it. So, okay, so let me try to do that. Let me focus on just this dipole approximation, and but one should not get confused by the fact that, okay, this is the leading term in the 1 over n, but if I take this ti.tj for finite n, because this is an exponent, then you expand the exponential, of course, and you get to all orders. You get all loop corrections. Not all of them, but you get corrections that appear at all loop order.
This is a one loop, so you haven't done a large n expansion.
Here, no, not finite n now. Yes, thank you, Adolfo. Okay, so you can show that, again, even at finite n, this is what it looks like if you just stay at this dipole approximation for the soft factor. So I'm just renaming all this, I'm calling it A. And then if you can just, for example, if you play this game of taking derivatives of this with respect to the Z, then you use the Baker-Campbell-Hauser looking formula, and then you have all those commutators. And now you look at this at the very first term. If you see this matrix A is just that over there. And if I take derivatives with respect to Z of this object here, you get this over here. So if just for a moment, let me close my eyes and you look at the very first term of this equation, this is exactly the Nishnitz homological equation that shows up, as this consistency equations in Wessel-Minowitten models, provided that you identify that k over 2n with the typical thing that shows up in the Nishnitz homological equation, where the k is the level and g is this Coxeter number. Okay, so the hope is that, okay, what if you can consider all these corrections as to be small in some kind of perturbative expansion? And this is exactly what the large n expansion does for you. So the hope is that maybe the infrared part, the universal infrared structure of nonabelian gauge theory can be seen as some deformation of Wessel-Minowitten. And so let me be a little bit more precise with my factors of n. So take again the dipole approximation. If you compute this at finite n again, you can see that there are only two terms, this one here, and this is 1 over n. You plug that back into this series of commutators, And then you get this, and you clearly identify that you have like a 1 over n expansion here. The bad news is that here you don't get the full Nishnitz homological part of the equation. So this A0, I'm not showing it here, but this is proportional just to the identity matrix. So you get this Nishnitz homological equation looking thing, but actually at leading order in 1 over n, this actually projects it to just like the diagonal part of the matrix. So all the nice features, all the non-abelian features of Nishnitz homological actually this is blind to that, at least at leading order in 1 over n. So of course the natural thing is to compute more things. We haven't done it, this is work in progress, but that seems like a fruitful approach, at least in my view. Let me just make a different observation, that you can still get this kind of expansion in other parameters. For example, we tried with going into some collinear limits, or even taking the cross ratio, which is SL2C invariant. That's a nice feature. And if you take, for example, the large cross ratio limit or the small cross ratio limit, you again see something like this. The nice thing about that is that now the full non-abelian structure of the Nishnitz homological equation does show up at leading order, but the price that you have to pay, of course, is that now this is only true in that particular limit. Okay, so that's the price you pay. Okay, so I was going to skip this. Let me just change a little bit subjects, but again, within the same subject of all loop things in non-abelian gauge theory. So let's study a little bit celestial amplitudes for the case of n equals 4 super-Young mills. Let me focus on the 4-gluon amplitude in the planar limit, which is known as the BDS formula.
Are there any low-dimensional toy models of this computation of the this soft factor or whatever? There you could do it to all like loops or something.
AVGM, things like that?
Or maybe 2 dimensions where you could get some all loop result at large n or something like that?
I don't know, maybe like Gros-Neveu models, things like that, are you thinking of, or no?
Yeah, no, just 2D Young mills or something, yeah.
I don't know. It's a very good question, of course, but yeah, I don't know.
Okay, and
okay, so I have until 6, right? Yeah. Or 10 to 6, yeah.
There is no IR divergence to dimensions, but there are boundary modes. Is that what you mean?
I didn't remember, but I was just wondering.
But there is no this is only for the IR problem.
Yeah.
So you have to have the angle that should be maximum.
Yeah, I guess you're right. Yes. Yeah, I guess you're right. Yeah, that's a good point.
I mean, the Wessel-Zumino-Witten model is the fatty Lagrangian QCD for the hadrons. Have you tried to connect hadrons with gluons?
No, I haven't. Yeah, I mean, that's a very good remark. Yeah. Thank you. Yeah, I haven't thought about it. Thanks. I mean, we can discuss later. Thank you. Okay, so in the planar limit of n equals 4 super-Young mills, there's this famous formula, the BDS formula. So basically what we tried to do here, I mean, we did with Hernan and Andrea, was, okay, can we compute this? This would be like a case of when we have a celestial amplitude to all loop orders. So that's what we did. So again, even though it doesn't look exactly the same as before, but it's the same form. And when you have the all loop amplitude and it's factorized into a tree level part, and then you see exponential of the infrared divergent part times another exponential of this Mandelstam's, logarithms of Mandelstam and so on and so forth. So if I wanted to separate it again into a soft part and a hard part, the soft part would be just, would be just that exponential. And the hard part would be this times that exponential over there. And then, well, of course, the big surprise of the BDS ansatz those days was that the hard factor also exponentiates. That was the big thing of that formula. Not only the infrared divergences exponentiate, the full thing also exponentiates. And of course, that's a very particular thing of the n equals 4 super Mill theory, and also in the fact that this is in the large n limit, so the planar limit.
It's only 4 points.
Ah?
It's only 4 points.
No, I think it's true for any points, right? It has corrections though. Like Alday and Maldacena found the correction starting at 6 points, but the exponentiation of the hard part, I think that persists to any, if I remember correctly.
Sorry, what do you mean? Everything is an exponential of a logarithm. So that you can compute it from the Wilson loop. I think that's true for 4 points, but at 6 points, the rational terms are not. But at 6 points, don't you have the symbols and all of that?
At 6 points, the exponent gets modified by this R function. The rest, I forgot the name, but you just correct the exponent. I'm sorry.
Yeah, that's what I mean. It's not exponential of the area.
Well, it's, I mean, the n equals 4 planar, you still have the Wilson loop.
Yeah.
Which you Wilson loop corresponds to all of this, which has its exponentiation feature.
Right. In the planar.
Not this, but there's a remainder.
Yeah. Remainder.
Right.
That's the. Yeah. Thank you.
Okay.
Okay. So if you play again the game of computing the Mellin transforms over the, we did the 4-point MHP case for simplicity, then, well, you get what you expect. You get a 4-point correlator, and then all the information about the theory itself and all the loop structure gets into this integral over here. And if you take a look at that integral, there's a minus sign there. There's a log of square and a log of square of these things here. So the convergence of this depends crucially on the sign of that. And actually, it was shown in these papers by Basso, Konchemsky, and Belitsky, Grodzki, and Konchesky, also a little bit before, that this object here, known as the cusp anomalous dimension, was strictly positive for all values. I'm sorry, for all values of the coupling. Sorry about that. Okay. So you could say that, okay, the very existence of the all loop celestial amplitude in the planar n equals 4 super Mill is owed to the positivity of the cusp anomalous dimension. We also showed that this it's the same thing happens for five gluons, and I guess you can do the same thing for higher point functions, but okay, it looks more complicated. So okay, so with that I finish the field theory part of the talk. Now let me go to celestial strings. I might take less than 50 minutes in total. So what's the motivation for doing strings on the celestial sphere? Of course, well, there are many motivations. Let me point out a computational one. In field theory, for graviton scattering, just Einstein-Hilbert gravity, at tree level, this is, for example, the MHV amplitude. This is what it looks like. So you see it has too many powers in the of the energy in the numerator. So that makes it the celestial, the Mellin transform actually blows up even at tree level. Okay, and the same thing happens with all other amplitudes in Young-Mills, QCD, at any loop order, except though for n equals 4 super means to all orders in the planar limit, as I just showed. But for the rest, field theory amplitudes usually blow up when you compute the Mellin transforms. But okay, here's part of the motivation for using strings that, if you recall, for instance, the open string amplitude for tachyons, the Veneziano amplitude, then if you go to the high energy limit at fixed angle, then it's exponentially suppressed. The same thing with closed strings. The Virasoro-Shapiro amplitude also has the same form. The factor here is a function of the scattering angle. So if you're at fixed angle and you go to the high energy limit, also known as the hard scattering limit, then you get this nice soft exponential behavior in the ultraviolet for open and closed strings. This was shown by Gross-Mende and then by Gross-Ibáñez for the case of any loop order, closed strings and open strings. And the exponential factor just merely gets modified by some numerical factor in the denominator of that exponent that has to do with the genus of the worldsheet topology. But again, you have this exponentially soft behavior at any order in the loop expansion in string theory as well. And this, well, okay, there's no proof, but there are many indications that this holds for any point amplitude, for any, endpoint amplitude. Also note, in order for this thing to be exponentially suppressed, this is done at fixed angles. So it's the same thing that you need in celestial amplitudes. You integrate over energies, but you want to leave the angles, arbitrary. So that's also a nice thing about strings. So at least from these features, the strings seem like a good testing ground for celestial holography, and of course the fact that string theory is a theory of quantum gravity, it's a consistent theory of quantum gravity, then even more. Let me give you the some of the computations, the first computations that you can do in a string theory, for example, for open strings. So now let me go to the type 1 superstring. The tree level amplitude, for example, for the MHV, actually this holds for any polarization structure. You have the Yang-Mills at tree level prefactor multiplied by just this string. So all the stringy dependence is here. And in this case here, this is pretty much the same as the Veneziano. It's just the Euler, it's very similar to the Euler beta function. So it's just that Mandelstam goes outside and then you have the Euler beta function. You can easily, if you use that representation of the beta function, you can easily compute the Mellin transforms, blah blah blah, and then you arrive at the what you expect, some correlator, some generic correlator that has to be there because of conformal covariance, but all the all the information about the stringy part is actually here in this integral, in this object over here, which is given by this integral. So notice that, this is an integration over the moduli space. So in the case of 4 points, for example, for tree-level open strings, you have the topology of a disk, and then you have, because of the SL2C remnant, residual invariance in the worldsheet, you can fix 3 of the vertex operators to any position you like, and you integrate over just one vertex operator. So is that degree of freedom the one that it gets manifested in this one integral over this variable x over here? Of course, this is known to many people in the audience, but let me just review it a little bit because it's a little bit important to what I'm going to say at the end. Okay, so as you see, I did an integral over the energy. So the moduli integral, the integration of the modular space of the integral amplitude of the string amplitude remains, and it just gets modified to this form. Okay, and this was done first by Stieberger and Taylor in 2018. So one important feature is that notice that because you're integrating over the energies, and the energies, let me go back to the amplitude, only appears in the exponent, and they get multiplied by alpha prime just to produce a dimensionless number. Now you integrate over the energy, so the amplitude, the celestial amplitude now has there's no hierarchy in the energies because you're integrating all the way from the deep IR to the deep UV. then this happens, all of the alpha prime dependence comes outside as a prefactor, and the rest doesn't depend on alpha prime, of course. Okay, so this begs the question, okay, we know that if I have a string amplitude, and if I take the low energy limit, I do the alpha prime going to 0 expansion, I know that I arrive at some field theory amplitude. And I know that if I take the string theory amplitude and I do the Mellin transform, and if I have the field theory amplitude, I also do the Mellin transform, then there should be a way in order to go from the celestial string to the celestial field theory amplitude. But how can you do that if now your parameter that you were relying on to take the low energy limit actually comes out as a prefactor? So that is the question that Stefan and Tomasz set out to answer in that paper. And so yeah, that's basically what I just wanted to say. I mean, what I just commented. You have the string, alpha prime going to 0 limit, you arrive at field theory. If I have a string amplitude, I take the Mellin transform, I have a celestial string, then what is the limit that brings me from here to here? There should be a limit because I mean, I could have gone this way. It would be weird if they don't commute. So what they found is that if you go into this kinematic regime just to the celestial part, so you leave the field theory prefactor intact. If you just do this trick, this mathematical trick, when you go to the limit, when this conformally invariant cross ratio goes to infinity, you can say that this is also the Regge limit, for example. Then you arrive at the field theory limit of the original string amplitude. Okay. By the way, we also make this little observation later on that if you take the opposite limit, you also recover that. But the origin of that is very simple. The original amplitude is actually crossing symmetric. S and T, S goes to T and T goes to S. So actually R and 1 over R are identified. So that's why you recover the limit in both extremes, when R goes to infinity or where R goes to 0. What happens with all this when you go to one loop? I'll just go maybe fast, but the punchline is that pretty much everything works the same, but a little, just a little detail. So again, at one loop, we're doing again type 1 string with SO32, Champeyton factors, blah, blah, blah. But just as a toy model to do celestial string amplitudes at one loop. Again, you have the same factorization, this nice factorization property. This is the tree-level Yang-Mills, and this is now the one-loop stringy factor. And now it has more structure. For example, it has a planar diagram and a Mobius strip kind of diagram. There's another diagram, which is called the non-planar, but let me just focus on this kind of a diagram first. If you look at Green, Short, and Witten, actually this is these two things come together, and the non-planar has a different coefficient. That's why it's treated differently. So let me do this. And then again, you see that in string amplitudes, even though the moduli integrals look very complicated, the energy dependence is trivial in that sense. And it's always like an exponent of the Mandelstam's in this in functions here. Here, this size are now combinations of the Jacobi theta functions. Okay, but I'm not going to say much about it. But this always is the case, and the origin of this is pretty much it's very simple. And it's external states always have the plane wave e to the order or time normal order of e to the I k dot x. So that's the origin of that. So that makes it very easy to compute celestial amplitudes for strings. Okay, so maybe I'm not going to bore you with all these details, but the same thing that happens at tree loop, at tree level, occurs also here. It just gets more complicated. Let me just point out that maybe in the next slide, this prefactor here. So if I put together the tree level and the one loop contributions, they get this form here. This is the tree level contribution. This is the one loop contribution that we just computed. And so there's a prefactor here, which is a gamma of 1 minus beta. Beta, I did not say what it was. but is the sum over all the scaling dimensions of the external particles minus 1, because the scaling dimensions have to be 1 plus I lambda, then you get that. So let me go back. So this is what it looks like. So you see this pattern here. You see here the pulses start at beta equals minus 1. Here they're shifted by I'm sorry, the pulses start at beta equals 1, right? So here the pulses are at beta equals 2 and so on. So you have that feature there. And this is very speculative, okay, but okay, let me just say it. So the coupling that organizes the loop expansion in the celestial in conformal basis for string amplitudes, notice that it always have this 1 over alpha prime in the denominator. So this is just a question. Could the loop expanded CFT be telling us something about the non-perturbative effects on the worksheet just because it's 1 over alpha prime? Okay, I'm not going to say much about it, but it looks non-perturbative in that sense. It may be not, but okay.
This is the superstring.
This is the superstring. That's
Equal 4.
I'm sorry?
D equal 10.
At D equals 10, but I'm preparing the states in 4 dimensions. So I'm like turning off all the 6 extra components. But it's internally it's in D. I'm sorry, in 10 dimensions. Compactify, yeah. Yeah, this I did not say, but the computation we did it in the usual toroidal compactification, the 6 torus, like in the early days. So, and with this, I think I'll be almost finished with. So, what if we ask the question? Okay, now how do you arrive at the field theory limit of the celestial amplitude at one loop? Again, we don't have that. We don't have that alpha prime. It comes out again as a prefactor, as you can see. It's an overall prefactor alpha prime here, and here's an overall prefactor over here. So the integrals over the moduli are here. So you don't have alpha prime at your disposal to take any limits in that integral in order to arrive at the field theory one loop amplitude. The same as in tree level. So we did that ideation. Let me just review a little bit the in momentum space. What happens is that you're integrating, so that is topology of a one loop open string. Here are the 4 vertex operators. This is the planar. The Mobius strip, it looks similar, but let me just show you the planar part. So you integrate over now you can only fix 1 vertex operator, so you have to integrate over the other 3. This is why you have this integration over 3 angles here. But also you have this extra moduli, which is the size of the whole of that open string one loop diagram. So you have to integrate over that. So as was shown by Neve and Shirk, if I remember, or yeah, Shirk and maybe Neve and Schwartz. So sorry about that. For the case of n equals 4 Brilliant Mills. Yes, this is Brink, Schwartz, Green. Yes, thank you. What you have to look at is you separate this moduli integral, and you go and you zoom in into the limit when that hole becomes very big and becomes like a ring, which makes a lot of sense because now that looks like a particle loop. So if you look at that contribution, I mean, if you take a look at the contribution that dominates in the alpha prime going to 0 limit, you see that this is the corner of the modular of the integration regions that dominate. And again, it makes sense because it looks like a particle loop. And okay, this is a bunch of details, but okay, you do this change of variables. I'm not going to say much about it. This relevant factor becomes that, and you expand in small w. This looks like it's a nice thing because it looks like a propagator on a circle, so everything starts to make sense. And then you arrive at this object over here. And this is precisely the one loop amplitude that you find in field theory, but it comes written in the not in the usual Feynman diagram way, but in the word line formalism, which is no surprise because actually the word line formalism was invented from the string theory formalism. That's why it's also called the string-inspired formalism of field theory amplitudes at one loop. Okay, okay, so I'm not going to say much about this, but it's all there. The same thing happens as in tree level, blah, blah, blah. And the main message is that now I didn't need to go into any Reggie limit in order to obtain the field theory celestial amplitude. So it appears regardless of any kinematic limit, as long as you just follow the same prescriptions that people knew from the 70s in order to arrive from string theory to field theory. So here we arrive at n equals 4 super Young Mills, as in that paper by Brink, Schwartz, and Green. But of course, I mean, there are ways in order to, if you want to arrive at just pure Young Mills, for example, with SU engaged group at one loop, for example, you can look at this type 0 string computations also, if you would like to do that. Okay, maybe I'll just, 10 minutes? Okay, okay. Maybe it'll just take me 5. Okay, now let me show you a very nice observation that Stieberger and Taylor did in that original paper of 2018 regarding celestial strings. So let me go back to the original string amplitude, or the string factor, basically. And let me just write it in this form. And this has been known even since Veneziano original's paper, this computation is here. So what if I want to take now the high energy limit at fixed angle, and I can do a saddle point approximation of this integral here. You get that exponential softness behavior, but in terms of the what is happening on the worldsheet, the saddle point equation, you see that it's dominated by just one location of the vertex operator on the worldsheet, and that location gets identified with a point in the celestial sphere because this Z is precisely, it's the center of mass angle in this, I mean, it's the center, is the scattering angle in the center of mass frame, but it's pretty much like it's just one point on the celestial sphere. So, in their words, in that paper, you can see that this, pins a point on the worldsheet with a point on the celestial sphere. But this is all a momentum basis. This observation could have been made in the 70s. So can you see this in the conformal basis? So after you do the Mellin transforms, blah, 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 you get that you again can do a saddle point approximation. Notice that this G is just the log of the previous thing. So this, okay, I didn't write it, but this F is actually what's inside this bracket. So all the saddle points of F, because G is log of that, are the same saddle points of G. So, and now you have to identify that what you have to take, the large thing that you take is the sum of all these scaling dimensions. You have to go to I infinity in the complex plane B of beta in order to arrive at the same conclusion. So the same dominant location as in momentum basis, but now in the celestial and conformal basis. And this is the end of it. So that was done for the 4-point case. Can you go to endpoints? So for example, consider the general endpoint closed string amplitude at tree level to start. And then you do the same, we play the same game. I go to high energy at fixed angle. So I take all this Mandelstams being large, but the ratios among them are fixed. That's why, and that translates into fixed angles. Then you can evaluate this thing using saddle point approximations. Of course, this has been known for a long time. And then you arrive at the same as the scattering equations discovered by, used by Cachazo, He, and Yuan a long time ago. And then this begs a question. Okay, these equations are the saddle point equations. So what they're going to give you a bunch of configurations on the worldsheet that are dominant in the high energy limit to compute that amplitude. So and this is the key observation, that all these solutions can be expressed in terms of ratios of the Mandelstams. That means pure angles on the celestial sphere. So this identifies a bunch of configurations on the worldsheet with a configuration of the celestial sphere. So if I give you a scattering of particles that pierce the celestial sphere, and then I want to compute the string amplitude in the high energy limit, the worksheet it is going to be dominated by n minus 3 factorial configurations, because the solutions to the scattering equations are actually n minus 3 factorial. So for each configuration of the celestial sphere, you have n minus 3 solutions on the worksheet. And this is what I'm saying here, that however this map does not seem to be a one-to-one. Of course, I mean, it's 1 and n minus 3 factorial. But that's a map, and one would like that map to be maybe a one-to-one map. I don't know, maybe that's... This is just tree level, yes. Again, there are many simplifications here. So the natural question is, can you find a regime in which only one, or maybe just a smaller set of all this n minus 3 factorial configurations are the ones that identify? Okay, so we're working on that with Stefan and Tom, and that's the end of my talk. Thank you.
Questions?
Yeah, so the answer is you can at MHV, yes.
I'm sorry, what?
You can at MHV, but not not next to MHV. So 4 dimensions, that map, that rational map from the sort of the world sheet. So this is just the scattering equations. The scattering equations underpin the twistor string, the ambi-twistor strings, all of these models.
Yeah.
And I guess it's well known as MHV.
Yes.
That map is 1-to-1, and so everything works beautifully. Next to MHV, it's 2-to-1. Next to MHV, it's 3-to-1. And but I mean, it's not a terrible thing. I mean, it's there are games we can play with that. But I'm just saying that to a certain extent, from the perspective of twistor strings, ambi-twistor strings, and so on, this is you've already got quite a lot of data there.
Okay. Thanks. So it's there. Okay.
When you do your computation at one loop,
Yes.
comparing strings to field theory, you said you could also do it in n equals 0. Right?
Yeah.
Now, in n equals 0, the coupling constant runs. So
Yes, I agree.
At which scale are you computing the coupling constant, since you're sending alpha prime to...
That's a good question. I mean, I don't know the answer, but I mean, can you just fix some energy and compute it at that energy?
Which energy? You're integrating overall energies.
I agree, yeah. I don't know the answer,
Have you computed the non-planar diagram, the one-loop non-planar?
Yes, but we had a little issue with that in the sense that in the non-planar case, so here, right, we integrate over all the energies, which are here, S and T, right? So in the planar case, you can see that in the entire region of integration, S and T, or what comes up, actually, it's here. Sorry about that. This came out because this combination of things here in the for the planar case. So for that integration region, which is ordered, which is not the case for the non-planar thing, this is like an integration of a simplex. In that simplex, this has a definite sign. So the integral converges in that sense. So if you do the non-planar thing, you have to break up that integration region in many parts in which each of these Mellin transforms converge in different places. So it's a mess in that sense. It's doable, but it's a big mess. Yes.
Okay, thank you.
I had the same question. Is this the Mobius strip case?
That's the planar, and this is the Mobius strip contribution.
So, change my question. When you wrote the soft part as a correlation function, the planar limit of the soft part is correlation function of screening operators in the Coulomb gas formalism?
You mean not string theory?
No, sorry. In the field theory, you have the soft.
Here?
Yeah. So these are screening operators, right?
These are what?
Screening.
String?
Screening operators.
Screening. Okay. Yeah.
Or like what people usually compute in the Coulomb gas.
Yeah, I think so. Yeah,
but it's special because you only allow for contractions between nearest neighbors.
That is correct, yes.
What is the reason for that? I mean, other than the Young-Mills?
I mean, I don't think I understand the question. I mean, what? I mean, the reason, as you just said, okay, it's just that.
Right, but if you didn't know the gauge theory computation, right? So I think you would like to postulate that the soft part, I mean, we know the abelian case is simple because it's a Goldstone mode that has a two-point function. And I find it very nice that you are proposing now that for non-abelian case, there is a non-abelian sigma model or something like that. Gives you this soft part, but except that you only allow for certain OPs or certain kind of contractions between nearest neighbors.
Yeah.
So, well, there is no underlying reason for that if you were to just write down a CFT.
No. I'm just pointing out.
But also, it's only in the planar limit. So, if you don't look
That's
at.
That's right. Yeah.
So if you look at finite n, then you can still.
If you go to finite n, then you get longer range interactions in this. I mean, you don't get these deltas. You get deltas and other stuff.
Right.
Yeah.
So is there a chance that the 1/n correction that you were describing as well is computed by this or not?
I mean, you can do the computation, yeah, but we haven't done it yet.
I see.
The matrix structure is complicated enough.
Even the one
but
over.
I mean, I don't see any obstacles why it cannot be done. It's just long, but yeah.
So I guess in that sort of three-loop part, you've already got some pretty. Sorry, now you've got that picture up. The three-loop part.
Yeah.
You mentioned you've already got some pretty interesting functions. Sort of polylogs there. Trilogs or something. I can't remember. Is there any? Have you come across any theory that can deliver those?
Can you say it again? The last thing.
Is there some celestial theory that could deliver the trilogs? In the three-loop part?
Yeah, I don't know. Yeah.
Okay. I mean, that'd be wonderful if you could find one.
I mean, we just looked at the first part, and then we kind of stopped, and then we're retaking the computations now. But yeah, we haven't. I don't have nothing to report on that in that sense yet.
Okay.
Yeah.
We wait.
The good thing is that it doesn't depend on the energy, so it comes out right away. So the melon is invisible.
It's a beautiful quantity.
Yes, I agree, yes. Yeah.
For the non-planar part, following up on Paulo's question, is
in here, not
in the string case.
In the string case.
Yeah. Is the divergence of the melon amplitude any worse than in field theory?
So you mean the UV or the infrared?
The UV.
The UV divergence for the non-planar. I think it's finite, yeah. I think it's only this is why the planar and the Mobius strip had to be put in a form such that their coefficients, that only happens for SO32, such that the divergences that come from Q near 0, which is the UV one, cancels out.
Because it was the IR one that obstructs having an answer as nice as for the planar case.
So the IR divergence?
Yeah. You were saying before that it's not such a nice answer in the non-planar case as in the planar case.
Yeah, but in the non-planar case, again, we didn't do the computation because of this mess with the regions of integration in which the melon converges and not.
Yep, I'm asking precisely about that because in the field theory you also have amplitudes that are, not convergent. If you take the melon, if you compute the celestial amplitude for that.
But
you can, amplitudes are distributions, and if you properly define them, if you find the celestial dual to Schwartz space for those, then you can, make proper sense of them. So I was wondering whether there's some, distributional sense for which you can make.
Okay, yeah, now I understand the question. Yeah. Well, yeah, no, I haven't looked into that, but I know what you mean. Yeah, thanks. That's a good question. Yeah.
Any more questions? Okay, with that, let's close today and thank Francisco again.